So today we're learning about E. E is an irrational number, right? Oh, that's pretty. An irrational number. It's called the natural base because it's found in nature. I didn't say that yet, but it's found in nature. A lot of populations that grow can be modeled by base E, better than any other base, okay? It appears in nature. So just like pi, which is 3.14, which is an irrational number, it's non-terminating, non-repeating. There are actually computers right now calculating the decimal digits in pi. E is also irrational, transcendental. It is 2.718. If you know it's 2.7, that's good. But it is also a non-repeating, non-terminating decimal. It is irrational. Okay? But it's not like the square root of 2 irrational. It's not like the square root of 3 irrational, both of which are irrational. We call those algebraic irrational numbers. It's not a solution to an algebraic equation. It just occurs in nature. Now, it has a lot of applications. It was studied intensively by my favorite mathematician, or one of them, my favorite mathematician, a Swiss mathematician by the name of Leonhard Euler. This is how you spell the name Euler, okay? Leonhard Euler. And since he worked with it so much, he gave it the letter that we use today. What's the first letter of Euler? E. So he gave it the lowercase e because capital E was already taken for energy, right? He was being humble too. So Leonhard Euler, this is what Leonhard Euler stumbled across E as. He stumbled across it as the limit, as n goes to infinity, of 1 plus 1 over n to the nth power. This actually equals E, okay? And this has to do with continually compounded interest. So sometimes E is also called the banker's number, in addition to the natural base. It's called Euler's number primarily. We just call it Euler's number, but it is the natural base. Now, let's talk about this real quickly, because I want you to be aware of what's going on here. As n goes to infinity, 1 over n goes to 0. The reciprocal of a big number is a small number. So the inside right here, 1 plus a small number, it's going to 1, but the outside is going to infinity. So this whole expression here is approaching 1 to the infinite power. But the answer is not 1. The answer does not settle down to 1 because inside is always a little bit bigger than 1. It's never equal to 1. It's always 1 plus a little bit more. And if you ever take a number that's bigger than 1 and you keep raising it to higher and higher and higher and higher powers, you might think it's going to get infinitely larger and larger and larger. But it doesn't settle down at 1 and it doesn't get infinitely larger. It settles down on 2.718281828, blah, blah, blah. It goes on forever. Okay, so that's the idea behind E. Now, just to show you that E is actually more important than pi for what we're going to do, let me go to the calculator face right here. You don't have to pull yours out. We're not going to use it today, but I want to show you. We all know how to get pi on the calculator, don't we? You use pi in geometry, and good for pi. Pi really is the star of the geometry class. But in analysis classes like pre-cal and even algebra 2 now, and especially in calculus, E is the base that shines more brightly. There are two places, well, there's one place to get pi on the calculator. If you hit second caret gives you pi. You see that? It's the blue feature on pi. You get 3.141592654. But E is actually on the home screen twice. If you hit second ln, which is to the left of the 4, you get E raised to the power of. E raised to the power of. That's what we're going to study today. We're going to study E to the x. But if you raise it to the first power, you get the value of E, 2.7, 1828, 1828. You might think it repeats like that forever, 1828, 1828, but it doesn't. The decimals get crazier after that. Or you could just hit, watch this, second division bar. If you hit second division bar, you get E the number, which is the same thing. So E is that much more important as pi. It shows up in two different shortcut places right there on your keyboard, whereas pi only shows up once. So as you move forward in your mathematical career, pi is important, but E is kind of the one that's going to shine most brightly moving forward. In fact, there is a formula called Euler's identity, which is my favorite equation of all time. Do y'all have a favorite equation, or am I the only nerd in here, huh? E to the pi I plus 1 equals 0. This is an equation that is not only true, but it relates pi to E, to the imaginary unit, to addition and multiplication and exponentiation, and the identity element of addition, which is 0, and the identity element of multiplication, which is 1. It relates them all together in this simple but beautifully elegant little equation. Okay, it's called Euler's identity. So there is a way to relate e to pi in a single equation. If I ever get a tattoo, I'm not going to just yet, but if I ever get a tattoo, like when I retire, this is the tattoo I'm getting. And no, I'm not going to get it on my arm or my shoulder. I'm going to get it tattooed on my forehead backwards, like ambulance. So when I'm driving in an automobile, people look in the rearview mirror, guess what they see? They see it forward, e to the pi I plus 1 equals 0. I'm that passionate about it. Okay? All right. That was a joke. I won't do that. I might get this tattoo, but I might get it like I don't know. I don't know where. I don't even know where I'd get a tattoo. That's why, like, I'd walk in. You want a tattoo? Sure. Where? I don't know. My forehead. Is that a good place? Right? I have no idea. That's why I'm not allowed in the tattoo shop. Okay. I'd end up looking like Post Malone. Not a good idea. Those things don't wash off, Post. So anyway, let's look at now e to the x. E to the x is now going to be our exponential function. And is it growth or decay? It's growth, okay? And that's because e itself is approximately 2.7. You don't have to know 2.718. If you just know it's a little bit less than 3, that's great. In fact, e is less than pi, isn't it? Because pi is 3.14 and e is 2.7. That's all you really need to know, okay? E is about 2.7. So the function will be modeled after exponential growth. All right, guess what's going to happen when we look at the graph of e to the x by itself? Certain things are going to be exactly the same. The reference point, which is the y-intercept, is still going to be the point 0,1. It's still going to pass through the point 0,1, just like anything of the form b to the x. The asymptote, which I'm going to put the h asymptote, it's going to be also at y equals 0, which is the same for all other exponential functions of the form b to the x. Guess what the domain is going to be for e to the x? All real numbers, just like it is for all other functions of the form b to the x, whether they're growth or decay. And the range is everything above the asymptote, which is the set of all y such that y is greater than 0. Or you could say y epsilon, parentheses 0 to infinity, whichever you prefer. Okay, now if you don't graph any other function but e to the x on the grid, you could just draw it like this. Okay, you draw it coming from the horizontal asymptote, which is at 0. You have it passing through the y-intercept, and you have it gradually increasing off to the right. And there's it. That's it. That could be the graph of f of x equals e to the x. I'm not going to check any other points to make sure that it's accurate. The actual graph on this grid would actually be a lot steeper. As it passed the y-intercept, it would actually curve up quite a bit. If you think of e as being kind of like 3, what would it be at 2? What would e squared be? E squared would be approximately 3 squared, right, which would be 9. So the actual graph at 2 would be somewhere way up here at 9. So in reality, it would actually be curving upwards very, very rapidly. You don't have to show that. I'm not going to be looking for any other point except the reference point, okay? So just draw it kind of nicely sweeping up as an exponential growth. You could draw this for any exponential growth function, and I'd be happy. But this becomes the new parent function for all exponential growth. Okay, now here's what we want to do. We want to see what happens when we graph e to the x and other bases like 2 to the x and 10 to the x on the same graph. It says to use the calculator, but I'm going to walk you through it without the calculator because you're going to be thinking a little bit more and the graphs will be more meaningful. So let's come off to the side here and let's give ourselves an x and y axis. Now the y axis you could draw like normal, but the x axis you want to draw a little bit lower than usual. Guess what all three of these functions have in common? They're all exponential growth. Good. They're all exponential growth. Okay, 2 to the x, 10 to the x, and e to the x, which means they all have domains of all real numbers, which means they all have ranges of everything greater than 0. Yeah, they all have y-intercepts. They all have y-intercepts, which are reference points at 0, 1. And they all have horizontal asymptotes at y equals 0. They all have the exact same thing. So let's go ahead and graph e to the x first. I'll graph it in purple, okay? I'll graph e to the x in purple. So it's going to have the horizontal asymptote on the x-axis. It's going to pass through the point 0, 1. And I'm just going to draw a nice exponential growth curve that sweeps up at just kind of a moderate pace. Now I'm going to call that h of x. Okay, and I'll label it in purple. I'm going to use 3 different flavors here so we can see the contrast. Now, That could be, again, the graph of any exponential growth function. But as soon as we start putting another exponential function on the same graph, now we have to show the relative steepness. So I'm going to switch to green here, and I'm going to graph f of x, which is 2 to the x. 2 to the x will also pass through the point 0, 1. Okay, it's an exponential function. 2 to the 0 is still 1. But here's what happens. Let's look to the right of 0 as x gets bigger. Which one's going to grow faster for large values of x? Something that doubles every value of x, or something that nearly triples? Nearly triples. So e to the x is going to be a bigger function. So 2 to the x, you could draw like this. It's going to grow, and it's going to go to infinity. It's just not going to go as fast. So there's f of x. Now, not only is it not going to go to infinity as fast, it's not going to go to 0 as fast. So it's going to look like that. So it's actually below the curve of e to the x on the right, and it's above the curve of e to the x on the left. It's less steep. Okay? It's less steep in both directions. E to the x goes to infinity faster, and e to the x goes to 0 faster. Okay, now let's pull out the red graph, which will be 10 to the x. 10 to the x has a y-intercept at 0, 1, and a horizontal asymptote on the x-axis. So it passes through the same point, 0, 1. But what grows faster? Something that increases by a factor of 10 each time, or something that nearly triples each time? Oh, factor of 10. So now for positive x's, 10 to the x is going to be much steeper. It's going to look like that. That is g of x. Okay, g of x. And not only does it go to infinity faster, it's going to go to 0 faster. So it's above on the right and it's below on the left. Okay, so g of x is actually steeper in both directions. So we got one that's less steep in both directions, that's 2 to the x, and we got one that's steeper in both directions, that's 10 to the x. Okay, so the only thing that they differ, that's what they have in common. How are they different? They vary in steepness. That's it. The bigger the base, let's say this, the bigger the base, comma, the steeper the graph. The bigger the base, the steeper the graph. But they all pass through 0, 1. Okay? So that's what you have to realize when you're graphing more than one exponential function on the graph at the same time. You have to show their relative steepness. All right, now let's look at part B. Now I have the same parent function, e to the x, e to the x, e to the x, but they are going to be varying in steepness because my a value is different. The a value is 1 for the first, 1/4 for the second, and 4 for the third. So 1/4 is going to be a vertical compression by a factor of 4, and 4 is going to be a vertical stretch by a factor of 4, and we'll compare all of them to e to the x. So let's go ahead and do this graph over here. We'll draw something very similar, just a y-axis, and then an x-axis that's near the bottom. And let's go ahead and graph e to the x again. I'll use purple. This time we're calling it f of x. E to the x is our basis. So what do we know about e to the x? It has a y-intercept of 0, 1, and it has a horizontal asymptote on the x-axis. And then I just draw it kind of moderately increasing like this, and I'll label that as f of x. Okay, and I'll use purple. Now, let's see what happens when I take the same function, and I don't switch bases, but I compress it by a factor of 4. Okay, if I compress something by a factor of 4, is that going to make it less steep? Yes, but is it going to change the y-intercept? Maybe. Let's look at the y-intercept of this one. If I type in a 0 for x, I get g of 0, which is 1/4 times e to the 0. E to the 0 is 1, so I get a 1/4. So, it actually lowers my y-intercept to 0, 1/4. Now, it still has the same horizontal asymptote. It's just compressed vertically. So that does affect the y-intercept. So now it's going to come through here, and it's going to look something like this. Okay, it's less steep, but it has a different y-intercept. And then the last one, I'll use red. if we vertically compress or stretch it by a factor of 4, let's see what the y-intercept is. H of 0 is 4 times e to the 0, which is 4. So now this one has a y-intercept that's vertically stretched by a factor of 4. So it's up there at 4. So now it comes in like this. And it still goes to 0. And that's the graph of h of x. So notice what they differ by. They have the same stuff as the other ones, but they differ. There are different steepnesses. They have different steepness, just like before, but now they also have different y-intercepts. Different steepnesses and different y-intercepts. So there you go. The top one is different bases. They share the y-intercept. They cross paths at 0, 1. And the next one is the same function, but what happens when you vertically stretch or compress it? Okay. Similarities and differences. I guess we should state the similarities here. They do have the same domain. They have the same range, and they have the same horizontal asymptote. And they're all still growth. They're all still growth functions. So that's what they have in common. Same domain, same range, same horizontal asymptote, just different steepness, just like before, but now the noticeable difference is a different y-intercept. Okay, so now what we're going to do is shift gears, and we're going to do what we did yesterday with different bases. We're going to do the same thing with base E. So it's going to feel very, very repetitive. If you understood yesterday's lesson and you've been paying attention all year long for the other functions, it's going to be very, very boring, maybe, perhaps. So maybe if y'all get too bored, maybe we can stop and you can share a joke or something. Yeah, and we can kind of liven it back up a little bit, like, oh, yeah, hot dog, I get it. Oven, right? Did the dog die? That's what you're wondering. Okay, so here is the basic form for a transformed e to the x function. We still have our a in front, which is still going to be your vertical stretch or compression, or an x-axis reflection, just like before. Now, for some reason, we switched to h and k. Yesterday, we used c and d, didn't we? I don't like switching to h and k here because the coordinate h comma k is not necessarily going to be your reference point, the old y-intercept. So I don't like h and k. So I'm just going to get rid of the h, and I'm going to get rid of the k. I don't know why we switched to hk there for no reason. Didn't use it yesterday, which was nice. So I'm going to stick with just the alphabet letters, x minus c plus d. I think that works fine. C is still your horizontal shift. And D is your vertical shift, which doubles as the equation of the horizontal asymptote at y equals D. That's nice. Okay? If you want to use H and K, that's fine. They're just letters. It doesn't matter what letter we call it. What matters is you know what it does to the graph based upon where it shows up in the equation. That's the important thing, okay? All right, so let's look at example 2. We've got our parent function e to the x, which is our growth function, so it is exponential growth. And we have this new transformed graph, which is 3e to the x minus 2 minus 7. Let's list the transformations, okay? So number 1, from left to right, what does the 3 in front do? Surprise, surprise, it's a vertical stretch by a factor of 3. We know that that's going to change the y-intercept. It moves it, stretches it vertically. What does the next thing do from left to right? Well, what does the minus 2 do for x minus 2? Right 2, that's going to change the horizontal value of the vertex or the y-intercept, the reference point. And then the minus 7 moves it down 7. Okay, so now we can talk about what happens to the reference point and the asymptote. The asymptote we have right away, don't we? I'm going to jump over to the asymptote because if we moved it down 7, there is I'm going to put an h in front of asymptote. There's a horizontal asymptote at y equals what if we went down 7? Negative 7. Yeah, negative 7, not positive 7, negative 7. And the reference point, I don't think that's a large enough blank to do the reference point. So here's what I would recommend for the reference point. It's nice to see the original reference point, which is the y-intercept, 0, 1. And then we'll move it to the new point. It's nice to see the original reference point because we changed them one at a time. And I can focus on where the 0 went, and then I can focus on the 1 where it went. So let's look at the 0. The 0 is the x-coordinate. The things that affects the x-coordinate is just the -2, isn't it? So if I move it right 2 units, where did 0 go? Did it go to -2 or +2? +2. Good. I went right 2 units. And then the 1, whoa, I wanted to highlight it there. The 1 has 2 things affecting it. The 3 in front first, and then the -7. And it has to be in that order, right? From left to right. So what happened to the 1? Well, 1 times 3 is 3. 3 minus 7 is -4. And there's your new reference point. So notice, this is why I don't like HK. If you call this H and this K, you might think the reference point is at HK, which would be 2, -7. Is it at 2, -7? No, it's at 2, -4. So that's why I don't like calling them HK. Boo, HK. Let's just call it C and D. Okay, and that's it. Now, it didn't ask us to sketch the graph, but I'm going to go ahead and sketch the graph because I like drawing things, like conclusions. Okay, so I'm going to come down here to -7, and I'm going to draw my horizontal asymptote. And I'm going to come over to the point 2, 1, 2, 3, 4, -4, and I'm going to draw my my new reference point, if you will, my old y-intercept. And now the function wasn't reflected, so it's still increasing. So I draw it coming from the asymptote, slightly increasing through that point, and then it takes off vertically. Boom. And there's the asymptote. Domain is all real numbers. Range is everything greater than -7. Growth function, yeah, we got it all. Once we have the graph, we have it all. All right, that wasn't hard, right? Are we bored yet? Let's wait till we get through example 3 before we stop for another joke. I'm not quite bored just yet. Any questions on example 2? Yeah. Yes. Any other questions on number 2? Or was that a number 1 question? A number 1. Okay. See, that was a joke. Ah, I should be on the radio, right? Okay. Example 3. Write the function based on the given transformation of the natural base E. Okay, so here we go. I'm going to switch to purple. Rhymes with nurple. The function is transformed vertically stretched by a factor of 2. So vertically stretched by a factor of 2. Right 4 units, up 7. So let's go ahead and give it a name. F of x equals, if it's vertically stretched by a factor of 2, we know there's a 2 in front, don't we? That's it. That's how it works for every function. And now it's base E. And then translated right 4. So is that x plus or -4 in the exponent if it's right 4? -4. So again, make sure you write your exponent smaller and elevated. And then up 7 is going to be +7 back on the ground floor on the same level as the E. It's written a little bit larger and lower. And that's it. Golly, that's it. Does anyone know what the range of this function is just without sketching it? The range? Does anyone know the range? Greater than 7, right? We didn't reflect it across the x-axis, so it's just a set of a y. So that y is greater than 7. Piece of cake. Oh, what's the domain? We can do it with our eyes closed, right? What's the domain? All real numbers. Did I do it okay with my eyes closed? Yep. Oh, man, they're not really connected. I should have opened my eyes. There we go. There we go. All real numbers. Letter B. The function f, let's call this one G. I'm tired of calling everything f. It's reflected across the x-axis. Ooh. To get something to reflect across the x-axis, what do we have to put out front? Negative. A negative, right? Now, it's also vertically compressed by a factor of 3. So what do we do with that 3? 1/3 in the front. Very good. That's a double A value. The negative is an x-axis reflection, which is across the asymptote to begin with, and then vertically compressed by a factor of 3. And now it's E to the up 9 units, so it's just e to the x. Don't forget the x. If there's no horizontal shift, it's still just x, and then +9 on the ground floor. Excellent. All right, the domain is all real numbers. I won't even write that down, but can we get the range without sketching it? What is it?
Y such that y is greater than 9, or less than.
Less than 9. Good. Because we reflected across, it now lives below the asymptote, which is at 9. So it's a set of all y's such that y is less than 9. Strictly less than 9. We never touch or cross the horizontal asymptote. All right, so good so far? So far, so good. All right. Anyone got a joke? Besides those two radio broadcasters in the morning? I knew you'd have a joke. What time of day was Adam created? Let me guess. It's not hot dog. No. It's not watchdog. Adam was created at what time of day? A little before Eve. Oh, see, that's good. That's good. If I get you the email to the radio station, will you send that one in? I could use that one in the morning, you know? That would make me chuckle instead of wince. Oh, a little before Eve. Yeah. Did you know that one already, Ransom, or did you just guess it?
No, I knew something Eve.
Yeah. I was thinking like apple o'clock or something, serpent o'clock, something to do with the Garden of Eden, you know? Forbidden fruit o'clock. No, a little before Eve. That makes sense. All right, example 4. Identify the required information. Okay, a function is vertically stretched by a factor of 3, left 2, down 8. We want to know where the reference point goes, and we want to know where the asymptote goes. I'm going to go ahead and write the equation here just to get extra practice. So it's going to be f of x equals vertically stretched by a factor of 3 means he has a 3 out front. E to the left 2 units means it's x plus 2. And then down 8 is going to be minus 8 on the ground floor. So for the reference point again, I'm not going to try and squeeze it in there. I'm going to do it underneath. 0, 1. Start with 0, 1, not 1, 0. Last period, I made a careless mistake because I was thinking of a funny joke, and I put 1, 0, and the joke was me. Okay, it's 0, 1. All right, so what do I do with the 0? I take the 0, and since I moved it left 2, it goes to where? Negative 2, yeah. And then I take the 1 and I triple it and then subtract 8. So what's 3 minus 8? Negative 5. Okay, so there's the new reference point. Negative 2, negative 5. And the asymptote, duh, is where? The h asymptote is that y equals what? Negative 8. This stuff's too easy. Too easy. Too easy. All we're doing today is the same thing we did yesterday. We're just trying to get comfortable using E. We're just trying to get comfortable using E. All right, the function is reflected across the x-axis. So I'll call this one g of x again to be different. Reflected across the x-axis, we already said is a negative out front. Vertically stretched by a factor of 4, so it's a negative 4 out front. E, and then up 3 units, so it's just e to the x, and back on the ground floor, it's plus 3. So it didn't ask us where the point went. Didn't ask us what the asymptote is. It asks us for the domain. Oh, easy, right? Double bar R. What did the pirate pay for his carn? How much did the pirate pay for his carn? You know, carn that grows in stalks in the field. Carn, like carn on the cob. Arr, carn. What did the pirate pay for his carn? About a buccaneer. Ah, about a buccaneer. Buccaneer. And then what's the range? Is it everything above 3 or everything below 3? Below 3. So you could say y epsilon, negative infinity to 3 parenthesis, or you could say the set of all y's such that y is less than 3. We reflected it after all. There it is. All right. And now the one that still gets people, writing the freaking equation. Woof! We did it yesterday. We're going to do it again today. Now, for our template, instead of using this, I showed you yesterday that we don't have to worry about the horizontal shifts because every horizontal shift can be accommodated by a vertical dilation and vice versa. A vertical dilation can be accommodated by a horizontal shift. So it's easier just to start with this template. A times e to the x plus d. All right, so that's my template for writing equations. My template for equation writing. And you're not going to be given that, unfortunately. You just got to know it. So we're going to get rid of the minus c. So I'm going to bring it down here, and I'm going to say my template is y equals a times e to the x plus d. All right, so there's really two things we need for this equation. We need the a value, and we need the d value. If I know the a and the d value, then I got my equation, right? One of those we can get directly from the graph, just by casual inspection. Which one? The d value. The D value is your stupid highlighter. I didn't mean to write with the highlighter, but it worked. This is your horizontal asymptote. Where is our horizontal asymptote based upon the graph? Now notice we're counting by twos on the y-axis. 2, 4, 6, 8. Who do we appreciate? Euler, Leonard Euler.
0.
Okay, I would go with 0, but if we're going to go to 0, see how it's already horizontal here? It's already horizontal. It's going to have a hard time getting from where it's at now to 0 unless we do that again, right? So I wish they had drawn the horizontal asymptote, but I think it's safe to assume that since they've already gone horizontal, that maybe there's a horizontal asymptote right there, which would cross at y equals what?
1.
1. I think it's safer to assume that the asymptote's at 1 rather than 0. So here's what I plug. I plug it in. I get y equals a times e to the x plus 1. Now all I got to do is find my a value. That's it. And to find the a value, all I got to do is use one other point on the graph. Just one other point. I need at least one other point on the graph. Well, look, we have a surplus of points. We have 2 points here. Does it matter which one we use? Does it really matter which one we use? Does it matter? It doesn't matter. Which one do you want to use? Me too. 3, 6. Stay away. Look at that. 5e plus 1. No thanks. Yucky, yucky. Gross, gross. I'm going to use 3, 6. So, yeah. Yes, yes. So I'm going to say at the point 3, 6. This is how we denote that we're going to plug in a 3 for x and a 6 for y. We say at the point 3, 6 colon. And I get 6 equals a times e to the third plus 1. Now, here's what you got to get comfortable with. This is the first time you've seen e as a number. E cubed is also a number. E is about 3, isn't it? So off to the side, if e is about 3, then e cubed is about 3 cubed, which is 27. Okay? So I'm going to just keep e cubed as a number. I don't want you to go to the calculator and type in e cubed, because then you're going to have this long, ugly decimal that goes on forever. But if you keep it as e cubed, it's exact. So all I got to do is subtract 1, and I get 5 equals, and I'm going to bring the e cubed to the front because it's really the coefficient of a. E is the number. How do I undo multiplying by e cubed? I divide both sides by e cubed, then I get a equals 5 over e cubed. Now, that is not the prettiest version of a, but guess what? It is a version of a. And all I got to do now is plug that back in up here to my working template with the d value of 1, and I get y equals 5 over e cubed times e to the x off to the side plus 1. And that could be your equation. The only thing I would possibly do is when I put it on the top line for the function, I might change y back to f of x just to elevate the name. So I get 5 over e cubed and then times e to the x plus 1. And we just leave it as e cubed. Now, let me walk you through another version of this equation. It's equivalent. Remember I said that vertical dilations and horizontal shifts can make up for each other easily, so you don't need both of them. Here's what I mean algebraically. Let's rewrite that as 5 times e to the sum power times e to the x plus 1. In other words, what do I do with the exponent on e cubed when I bring it from the bottom to the top? What do I do with it? When I move a factor from the top to the bottom or the bottom to the top, I have to do what with its exponent? Make it negative. Yeah. So an e cubed in the bottom is the same as an e to the negative third in the top. Why would I want to do that, you ask? Well, looky here. Now I have e to the something times e to the something, right? What does the rule say? When I'm multiplying and the bases are the same, what do I do with the exponents? Well, when they're multiplied, I add them, right? I add them. If they're divided, I subtract. Now, one of them happens to be negative. So I end up with negative 3 plus x, which is the same as x minus 3. Is that a better looking version of the answer? I think that's a better looking version of the answer. I don't got that funky a value of 5 over e cubed. Instead, I just got, oh, it shifted right 3. But that's what I'm talking about. A vertical dilation by a factor of 1 over e cubed is equivalent to a horizontal shift to the right by 3 units. So it doesn't matter which one we put up there as the function. On a free response, I would take them both. Okay. If this were a multiple choice question, maybe I have to put it in the second version instead of the first version. That's why we studied the rules of exponents in isolation. So we could do something like this and be like, oh, that's no big deal. We got this, right? All right, now, the domain, again, with our eyes closed is what? Ah, I need to practice with my eyes closed. That didn't quite work. I better keep my eyes open. All real numbers. And the range, is it everything above 1 or everything below 1? Everything above 1. So the set of all y's such that y is greater than 1, or if you like interval notation, y epsilon, parentheses, 1 to infinity. And that's it. We're done. You met e to the x today, or you met e to the day, the natural base, also called Euler's number. Euler's number. Leonard Euler. Leonard Euler. It looks funny. It looks funny because it's Swiss, but it's pronounced Euler. Trust me. Everyone wants to say Euler, Euler, but it's Euler, Euler. If you called him Euler, he wouldn't reply to you. He was also blind in one eye. Oh, you want to know a funny guy? Euler was a funny guy. He was actually more productive after he went blind later in life. He worked by dim light, and he was very productive, and he was always working, and he lost eyesight when he was like old. He was like in his late 50s, early 60s, I forget, when he lost eyesight in one of his eyes. And get this, after he went blind in one eye, he was the most productive he'd ever been in his entire career. And people are like, that is bizarre. How are you more productive after you lost sight in one eye than before? How'd you do that, Euler? And you know what the funny guy said? He said, it was easy. I was less distracted. Less distracted, right? Because he had half as much to look at, right? As if that other eye is like a chameleon. It's just looking at its own stuff. But that's pretty funny. You got to admit, I was less distracted. I only had one eye instead of two. That's a good joke. That should be on the radio. All right, we're done. You have tomorrow to work. Good luck on your STAR test. And then these are both due Thursday morning. We are going to review on Thursday, and we're going to quiz on Friday, 13.1 to 13.3.